You know, there are points in your life when you feel you've arrived, you know, at a high point. It's not so much a chair in FOCS, but 50 people have done it before. But introducing Christos at a FOCS plenary, who's done that? Okay. Actually, a few people have already. So, I made 2 slides, it will take 3 minutes. The man needs no introduction, he doesn't even have a badge. But this will take a minute. I tried to dress up like him. So, Christos, you've definitely you've read something by him, you've based some work on things he's done, and maybe even heard a talk by him. Yeah, so in Mr. TCS for the last 6 decades, it's complexity, yes, anti-completeness. Treating TSP is anti-complete. But also, PCAD, PLS, Max SMP, things that had no place 30 years ago. Why did he bother to define this? We know now. Price anarchy, internet, networks, gameless computation. The lens of computation broadly. This is a field that we must share with others. These are insights not just for us. Databases, information retrieval markets, biology, evolution, brain, who knows what next. Okay, all this you know, or most of you know. What can I tell you that you don't already know? Okay, I'll try. That's foundational research, cutting-edge research. You can ask him anything, try him great. Okay? You want to know why your research is exciting? Ask him. You want a guided tour of complexity, of language and thought, of ancient Athens? You want a backup singer for your band? He's your man. The joy of doing theory. Actually, it's more than that. I think it's the exhilaration of doing theory. So let's welcome Christos.
Thank you, Sandor, and thanks everybody. Thanks to the organizers for inviting me. This is fantastic. I'm going to tell a story to my family. Okay, it's one of the best of times. Right? So, I want to start by remembering Luca, a brilliant theoretician, one of our best, friend. Above all, a great teacher, all of us, to me. And I want to stay silent for a few moments to remember. And I want to start by saying that my title is redundant in the following important sense: that we don't know how to compute without dynamical systems. Okay? If you think about it, the chip is a dynamical system of silicon and copper atoms and electrons. Okay? And the only reason why we can compute it is that we have managed to define some stable attractors that correspond to register value. And and I'm going to say a few times during my talk that I find it rather surprising that there is no 10 times more work, this year's work on dynamical systems than there is. So there is some. Good, great. So, to our main order of the day, which is Nash. It is really the idea that is at the root of modern economics. I'm going to argue about this. Okay, so you see, we all prove theorems. This is, our job is to prove theorems, and all of us have asked ourselves, can a theorem change the world? Okay, and this theorem did. Okay, it did change the world. First of all, it changed modern economics. it was adapted immediately. It gave birth to game theory, and it was immediately adapted as its default concept, solution concept, like prediction at large, the meaning of the game. Okay, what the game means. I mean, if you ask game theorists, they will tell you, well, it's a set of Nash equilibria, because that's where the game will be played anyway. Okay, it is elegant, it is convincing, it is universal, extremely important. Okay, so every game has one, and that was Nash's theory. I don't know how many of you know this, but it inspired Arrow and Debré to solve the price equilibrium problem, okay, which had been open for 75 years by then. How do I know? Kenneth Arrow told me around the same time in 1984 when he suggested to me that I should work on the complexity of Nash equilibrium. He did. Okay, so that's another man that I'm missing dearly. It is a powerful conceptual tool in economics research. Here's what I mean by that. That when an economist nowadays, or since 1950, thinks about an institution, a market they're designing, and so on, they have the luxury, the license to stop and say, okay, let's see what happens at equilibrium. And nobody will ask them, what do you mean by equilibrium? Okay, it will be there, it will exist. Okay, so this is the important contribution of the Nash equilibrium, the notion of equilibrium, Nash equilibrium in economics. And as the brilliant economist who blessed us with his presence and talk yesterday have said, the Nash equilibrium lies at the foundations of modern economic thought. Okay, and I believe he means the previous bullet. Okay, that it's a theoretical tool in economics. It's the theoretical tool par excellence. But since the 1990s, when economics game theory came under TCS scrutiny, it has, its fortunes have started to dwindle a little. Okay, because it does mix well with computation. For example, it's intractable. Okay, even for two-player games. All right, I mean, this is sort of 20 years later, I was able to carry out the mission that Ken Arrow bestowed upon me. So it's intractable, but I mean, between I don't know if you know this story. When Nash proved his theorem, he was last year PhD student at Princeton, and von Neumann was a famous professor of mathematics at Princeton. And von Neumann looked deep into his heart to find the most kind and generous words to encourage a young man who had come up with a great result. And this is what he came up with. Okay, so true story. Okay, and what is amazing in retrospect, the man was right. Okay, and when I say about von Neumann, the man, I mean the man. Okay, so here because the Nash equilibrium has problems with computation exactly because it is just fixed point. It is a fixed point, a Brouwer fixed point, without extra redeeming features. Okay, without any structure that helps you. All right, but I'm not sure that so. Generic fixed point, that's what we call PPAD complete these days. Okay, right? Okay, good. It took us 50 years to decipher von Neumann's enigmatic diction, but we did. Okay, so good. Okay, but I mean, between you and me, is intractability always really bad news? Okay, how you convince an economist? I mean, they all know of somebody who makes an honest living by solving intractable problems, right? I mean, why does it care? Okay, indeed, in practice, there are people who argue. I disagree that this is true.
But the Nash equilibrium is not a practical tool, it's a theoretical, okay? And for theoretical tool, intractability is lethal, okay? It is as if, for example, Roger Milestone himself said that nobody would take seriously the Nash equilibrium without the universality theory. And basically, intractability hurts universality, okay? It means that it's as if Nash's theorem says that if the complexity world is as it is, then almost all games have Nash equilibrium. Okay, you see what I'm saying? You know, basically, for all practical purposes, the Nash equilibria are out of reach. All right, for some game. Okay. And a second strike against the Nash equilibrium is that it's not unique, as it's famous. And I am in slide 7 of my 6 or something of my talk, and these are my 5th and 6th Nobelists. Okay, so these two people wrote a book trying to fix the problem. Okay, and basically the main proposal of the book is that here's how you select an equilibrium. You start with a very simple game where like matching pennies, and then you slowly deform it into the game at hand, and you follow the equilibrium, and that's your equilibrium. Okay, the one that you find. And the point is that this problem is p-space complete, okay? And we pointed this out later. Okay, so I mean, it gets even uglier if you insist on uniqueness. All right. So if you tell this to economists, chances are that somebody will tell you, well, fine, but the players will eventually get there. Okay. And frankly, if this is true, if there are credible behaviors like polynomial time behaviors that eventually polynomial time leads to Nash equilibrium, my criticism for Nash equilibrium would be gentler, okay? But the truth is that all known learning dynamics in game theory, and there have been over the past 7 decades, there have been probably many dozens of them, many dozens of proposals of the dynamics. And it was clear that the intention of the proposal for game dynamics of each proposal is to lead to the Nash equilibrium. Okay, for example, the first one was in 1950. Okay, fictitious play. But literally many dozens, and all of them do not lead to Nash equilibrium unless the game has 2 strategies, and or one player has 2 strategies, or it's zero sum, or it's coordination, or something like that. Okay, so it does not. For most games, it does not lead to Nash equilibrium. Okay. So this must be an important problem. Find a way to assign to each game a dynamical system, continuous or discrete time, such that the dynamics always converges to the Nash equilibrium and stays there. Okay, I'm not going to accept dynamics that they start at the Nash equilibrium and they feel uneasy. Okay, they move away. Okay. All right. Okay, good. Guess what? Here's the theory. There are games for which no such dynamics exists. Okay. I call it theorem 1 because of the following. Georgios Piliouras and I have been thinking about this for more than 10 years. Okay, have been writing about this for more than 10 years. But it was like marching in place. Okay, for 10 years. Not much was happening. And the last 15 months. There were 3 theorems that were proved that completely changed the landscape. It is the story of these 3 theorems that I want to tell you. All right, that's one of the theorems. The impossibility theorem. There are games for which there are no Nash convergent dynamics. Not polynomial, of course, but no Nash convergent dynamics. And before that. Can you see that this picture? Okay, that is not important. I have to define for you. I have to talk a little bit about dynamical systems. Okay, and basically, what's a dynamical system? A continuous dynamical system. Some people call it semi-flow. Is a mapping from the real integers to the space, continuous, but also has the translation properties that makes a trajectory make sense. And or otherwise, it's basically ODE, a direction of speed of motion at each point x. Okay, so that's two ways to define it. And the discrete version is even simpler, a continuous function that maps the space to the space. All right. And the interesting fact here is that sort of, I'm not going to mention it, but it holds for everything I'll say here, is that the math of the two coincide unreasonably often. Okay, even though they seem very different mathematical objects, they are not. Okay, they are extremely parallel mathematical objects. Good. So, where do the dynamics converge in the dynamical system, and what does this mean? Okay, so the tradition says either to a fixed point or to a cycle, or we have chaos. Okay, this is the conventional wisdom. Now, between you and me, fixed point or cycle, a fixed point is a special case of a cycle, right? So let's call it, it's either a cycle or chaos, okay? And we're going to get rid of one, okay? So, good. So, around the 1900s, there was the Poincaré-Bendixson theorem that basically says in 2 dimensions, only cycle, okay? People didn't know about chaos except for Poincaré himself. He knew about chaos before in the 1900s. Okay, so and the reason is that it's very simple. That the orbits, the trajectories cannot cross in 2 dimensions, right? Obviously, and so they discipline each other into submission. Okay, and therefore they have to behave well. Right? That's the main reason. Good. And for almost a century, mathematicians agonized with the question, but what happens in 3D? Okay, for 100 years, for 80 years, the field was suffering of Poincaré-Bendixson envy. Okay, they were studying, they were sort of they were nostalgic of the nice sort of regularity of the 2 dimensions. Okay. There is a way to express it by combining 2 masterpieces of the English literature. Okay, so it's like Flatland as Paradise Lost. Okay, so and what happened? It had this had a very happy ending. In 1984, Charles Conley proved an amazing theorem. Okay, there were people who were of course standing on the shoulders of other giants, and he proved that there is only one kind of limit. They didn't call it like that. He called it the Conley cycle. He called it chain recurrent sets. Okay, and any dynamical system converges to the Conley cycles, guided by Lyapunov function in the best and most orderly possible way. That's an incredible theorem. It's called, Conley did not call it that, but it's called by everybody else, the fundamental theorem of dynamical systems. Okay, so it completely resolves this question. They will cycle, but you have to redefine cycle. Okay, the cycle now is a Conley cycle. And what is a Conley cycle? Points A and B are on the same Conley cycle, they're chain equivalent if for every epsilon there is an n, so that you can go from A to B and back by alternating between the dynamical system, if it's decreed by a jump, if it's continuous by following it for one unit of time, and n intermediate epsilon jumps. Okay. In other words, Alice tries to convince Bob that he's on a cycle by manipulating his round of error. Right? It has this nice CS interpretation. All right, so this is the basic fact that I'm going to use throughout the talk. Okay, that all dynamical systems converge to such a cycle, and the sync such cycles are the fate of the dynamical system. Is it clear? Okay, marching ahead then. So let's back to the impossibility theorem. Let me give you a proof sketch. It would be the ridiculously short proof sketch. It starts with a previous attempt. I mean, these three people, Benaim, Hafbar, and Soren, a decade earlier had tried to attempt the same theorem, and they came up with the right idea. A particular game that had been used ages ago by Kohlberg and Mertens. This is a variation of the 3x3 game, a variation of rock, paper, scissors. It has sort of a remarkable property. It is highly degenerate, okay, in the two-player game sense, which means that it has too many, like in linear algebra, it has too many coincidences for its own good, okay? And as a result, the set of Nash equilibria is a continuum. And it's not just any continuum, it is a hexagon in 4 space. Okay? And then a page of algebraic topology tells you that it's impossible for any dynamical system, continuous or discrete, to converge to a ring. Okay? And that's it. All right, so that's the impossibility theorem. How about approximate equilibria? Well, in the same in the same paper, we have the following theorem that for all small enough epsilon, and that it doesn't have to be too small, there is a set of games with positive measure, such as this is ostensibly a stronger result. Positive measure. I mean, there I showed you one game. I mean, so here it's a positive measure, such that in these games, the no dynamics converges to the epsilon approximate Nash equilibrium. Okay, and the quick proof is this. Okay, that the epsilon approximate Nash equilibrium in the same game look like this. Okay, so this is a two-dimensional projection of the four-dimensional body. All right, and therefore they have a hole. They retain their genus from the original problem, and therefore they cannot be the target of the fate of any dynamical system. Okay. Good. Okay. But how about non-degenerate games? Okay, the game theorists know that degenerate games are sort of measure zero. You never see them in game theory practice. That's a fair point. Okay, because it turns out that in any non-degenerate game, Nash convergent dynamics always exists. Okay, so we need a non-degeneracy, obviously, to prove. Okay, what happens there? There are several types, and I'll mention 3 types. One type is the following. One type of Nash convergent dynamics is find a Nash.
Did you say again what made the last game degenerate?
Not easily. Okay, so it's if you try to write the equations for the Nash equilibrium, this matrix is degenerate in many is not debatable in many places.
So we just computed by like epsilon, but they also met.
Yes. It will go away. Yeah, but this hole will not go away.
Oh, we have the hole.
They will have the hole. Yeah, that's why I told you that the second theorem holds for a ball. Okay, good. But I mean, but the main theorem about the Nash equilibrium is in danger, is in jeopardy now. Okay, so here is how the narrative continues. We know of 3 types of such. So the first type is head to the Nash equilibrium, and you have to head to the right speed, which is sort of like proportional to the absolute value of the gradient. So when you are near a Nash equilibrium, you slow down and then you stop and then you start again. Okay, so in other words, it does converge to the Nash equilibrium. The downside is you can do this in locally polynomial time computable only if PPAD equals speed. Okay, that's a theorem. It's not immediate. Okay, you can construct. You need to in order to construct it. You need, but you can prove that you need to do that. There's no other way. Another one that has been shown in the literature is the domain, sort of, you know, the set of all mixed strategies can be partitioned into polytopes so that there is one Nash equilibrium in each polytope, and you can solve the problem in each polytope and then reconcile at the boundaries. Okay, and this is possible only if P equals NP. Actually, if P equals something higher in the hierarchy. Yeah.
What's the local polynomial family?
Sorry?
What's the local polynomial?
Okay, by this I mean that I'm looking for dynamics, which sort of, you know, if the player if the players are at a particular point, they can compute from this point where to go. Okay?
Without memory?
Yes, they look at what where they are and they go. I mean, dynamics is memoryless. Okay?
Yeah.
Okay. Good. All right. Type 3. Any dynamics together it's the Lyapunov function, and we know that there's going to be one. Okay. Now, if it converges to that equilibrium, it's going to have a Lyapunov function. So give me the dynamics and give me the Lyapunov function. Downside. It is locally polynomial time computable only if PPAD equals CLS. That's something we proved recently with Georgios and we haven't published. All right. Okay. And the conjecture is that if local polynomial time computable Nash convergent dynamics exists for all the general games, then PPAD equals CLS. All right. And I strongly believe in this conjecture, but I have trouble proving. We have trouble proving it, and I can actually recount one form of this trouble. Okay, you know, if there are any proof theorists in the audience, I sort of, you know, I need to see you. Okay, you know, and you know, here is the only way that I know how to prove something like this is the following. I mean, I have talked to Oliver Korda about this. The only way that I can prove a theorem like this, the conjecture like this, is the following. It's by reductio ad absurdum. Okay, you know, I assume that there is such a polynomial time algorithm, and I interrogate it. I interrogate it again and again for a polynomial time, of course, dynamically. So you know, and until I get enough information to find a Nash equilibrium. Okay, I can't do this. Okay, this is impossible because I have an oracle which, given any game, can mislead such an interrogator for an arbitrary polynomial without yielding any useful information. And in the end, I say, wait a minute, where is the dynamics? I say, here is the dynamics. So I can construct such an oracle, and I don't know what this means. Okay, it means that I cannot prove it the way I know how to prove it, but I mean, maybe there are other ways. Okay, good. Marching on. Well, so it seems that Nash equilibrium is incompatible also with dynamics. And this has to be bad news for the dynamics, right? Or is it the coup de grace for the Nash equilibrium? Okay. And cool, I mean, okay. So is the time to replace the Nash equilibrium by a new solution cost based on dynamics, on player behavior? Okay. In other words, the economists say, but the players will eventually get there. Okay. And the answer, no, they're not going to get there. Think again. Why instead don't you think that the meaning of the game is not the Nash equilibrium, because the players will not go there, but the place where the players will go? Let's call this the Nash equilibrium. Let's call this the meaning of the game. Is it clear? And in fact, back 5 years ago, when Georgios and I had been publishing about this point of view without having all these results, the people who were doing AlphaGo then came in contact with us, and they told us that this is exactly what they use as the meaning of Go. The meaning of Go is not the rules, but it is the dynamics of play between their best players. Okay, and where they go, the limit of the dynamics of noisy replicator dynamics among their best players. Okay, and in fact we have a paper in Science how's the journal called? From back then with these people, and they hired George Pilios. So forward dynamics. First of all, which dynamics? Let us fix the replicator dynamics, which basically is the most natural dynamics, the no-regret dynamics, gradient descent, multiplicative weights update in the limit, okay, as time becomes more and smaller. It's very natural, move along the gradient. And a big plus for economists is that it makes economical sense, okay? Economists will not trust the dynamics where zero utility matters, where there is zero utility. I mean, Roger Myerson was very interested in this yesterday, okay? So if they tell you that if I give the same number to everybody, the game changes, they say, thanks a lot, that's not for me, okay? And also currency, okay? I mean, if I solve under, it's closed under a fine positive affine maps, okay? That's also, by the way, what I'm going to tell you holds for a much broader class, which we haven't yet delineated, okay? So our work. But I mean, I'm going to use the replicator dynamics and the noisy version I'm going to do this later. So where does the replicator dynamics end up? We know the answer. By Conley's theorem at the sync Conley cycles of the dynamics. Okay, so you know that's what dynamic systems theory tells us. For example, matching pennies. It has one sync Conley cycle. It's the whole graph. Okay, it's a whole domain. The other 2x2 game coordination has 5 Conley cycles. They're all points, of which 2 are sinks. Yeah, no surprise. But how can we compute them in the general way? Okay, that's the problem. It looks like a terrible problem, okay? Because, for example, are there finitely many of them? We don't know. Okay, dynamical systems are known to have infinitely many. And suppose they're finite, are they computable? Dynamical systems are known to have incomputable attractors, right? So it looks like we're lost. So what we do is we are looking for a convincing combinatorial surrogate of the sync Conley cycles. Okay, and what are they? So this suppose that this is a game. Notice that the column player would like to change. Okay, that he wants to go from here to there. Okay, not exactly, yeah, and then oops. Okay, and then the raw player wants to change, right? I mean, so that, and basically what I'm saying is for many games you can create a graph, all right? By basically it's called a better or equal response graph, all right? Or preference graph. That's how Oliver Bigger wants to call it. And in fact, from the graph you get to a Markov chain because you label the edges of the graph with numbers, the differences, okay? And then you normalize that from every node, okay? The outgoing edges have to add to 1. And that gives you a Markov chain. And this Markov chain is the replicator dynamics when started at a node. Okay? So if we start at a node, we sort of know what happens, all right? I mean, but we don't start at a node and we're going to fix that. Okay, good. So these the Conley cycles here are the sync equilibria that were defined at this conference 9 years ago, and basically they're the sync strongly connected components of this Markov chain. They're called the ergodic components of this Markov chain, right? So these are the sync equilibria. And these are the fate of the game if you start from a node. Okay, and we sort of knew that, okay, but we didn't know what it has to do with the more general dynamics. But is there a relationship? We have our goal, we have a combinatorial surrogate. Are they related at all? Okay, so here comes the second theorem. There are many to one correspondence in that each single Conley chain cycle contains one or more single equilibrium. Okay, so essentially they're the same. Okay, so dynamics have finitely many. The attractors are finitely many. Okay, so we have done that, and we're going to see that they're computable. Okay, is the correspondence one-to-one, which we would love. Conjecture, it is for 2 players. Fact, no for 3 players, but we suspect in a superficially and tractable way. Okay, these are results by Oliver Brickell. Oliver is now my PhD student at Columbia, mine in Michalis. Good. All right. So, question of conscience. Okay. What is the game for you? Is it the specification of an intractable Nash equilibrium selection problem? Or is it an algorithm that maps a distribution over mixed strategy profiles, the prior of agent's behavior, to a distribution over a set equilibria, of single equilibria, the various possible outcomes of the game? In other words, I propose that the meaning of the game is where the players are going to go. And this is a mapping from a prior to a limit. And the limit should be over the Conley cycle. Okay. And in absence of a clear picture of over the synchronetic component. Okay. So this identifies an important computational problem. Given a game in canonical form, I remind you that the graph that we define, the better or equal preference graph, has tie edges, right? And these tie edges, they have intensity epsilon, okay? So, in other words, they are traversed with infinitesimal probability, okay? So they slow down, in some sense, the Markov chain, all right? So, given a game in canonical form, compute the limit distribution of the replicator dynamics over single equilibria when started at a given prior. So that's what we want. And we have the third theorem, which was very recently proved, the mapping from a prior distribution over pure strategy profiles, okay? We want over mixed, but we solve the problem for pure. To the limit distribution of the replicator dynamics over single equilibria can be computed in almost linear time, okay? This is a very complicated and if I may say so, clever algorithm. And the reason is the epsilon edges, okay, which basically they turn over the head everything we knew about strongly connected components, okay, and force you into a long dance of eliminating nodes one by one, and finding dynamically the new strongly connected components in the graph, okay? And by good fortune, this dynamical problem can be solved in almost linear time, okay? Good. So that's theorem 3. But theorem 3 is about pure strategy profiles. So computing the meaning of the game starting from mixed strategy profiles. Noisy replicator dynamics is multiplied weights updates now with non-zero, discrete time, with epsilon Gaussian noise added at each step, a very small Gaussian noise added at each step, and with the added rule, if the result is outside the domain, project back to the boundary and stay at the boundary. In other words, you have lost this dimension forever as happens with evolution. Okay, so if you lose an allele, if the population loses an allele, it will never get it back. Okay, unless it's very lucky. Empirically, it converges to the pure node rapidly, and combined with theorem 3, the meaning of the game, the mapping from a prior distribution over the prior distribution to a distribution, a prior over mixed strategies, the distribution over a single equilibrium can be computed empirically very efficiently. Okay, so we have used this algorithm to solve games with tens of thousands of pure strategy profiles. Okay, so and in other words, compute convincingly a mapping from any prior who are given to the distribution over the sink mass equilibrium, over the sink the sink equilibrium. Good. All right. Among the many open problems, what is the precise sense of it? In what precise sense is the correspondence between sink equilibria and sink Conde cycles morally one-to-one? Okay, as I promised. Okay, that it's not one-one, but it's not in an intractable way. Prove that the noisy multiplicity of the weight update dynamics. This is a very interesting problem in applied probability theory. I think. Okay, so Pillows and I have been working on it for a long time. Prove that the noisy multiplicative weight update dynamics converges to the single equilibria in polynomial time. It does so empirically. Polynomial, of course, in 1 over epsilon, and the side of the game. And identify, delineate the much broader class of dynamics for which all of the above holds. Okay. And to summarize. Oh my God! I've left. I was too big, but that's okay. It's good to have time. The Nash equilibrium is plagued by computational shortcomings. Game dynamics provides a powerful new way of redefining the meaning of the game. It suggests a novel solution concept, the sink equilibrium, that seems free, novel, but okay, of course, 9 years here at FOCS, it was first defined. The sink equilibrium that seems free of computational downsides. So Gemans and Tal defined it in the context of the price of analysis. Okay, so here we are using it for redefining what the meaning of the game is. Now, one thing I want to point out is the following. There is one uncontroversial solution concept in game theory, and that's the pure Nash equilibrium. Okay? If a game has a pure Nash equilibrium, nobody looks further, okay? Leave me alone, I understand this game, okay? Now, a mixed Nash equilibrium is a compromise. It's a generalization of pure Nash equilibrium that always exists. If you think about it, the single equilibrium is another different generalization of the pure Nash equilibrium. That always exists. Okay? You realize that a single node is a special case of a sink equilibrium, right? I mean, it's when it's a Nash equilibrium. So, a very interesting and intriguing question, which we have been thinking about for a long time without much insight. Okay, it's one of these open-ended questions that you can solve. You can write 10 different papers, by taking different paths. Is what is the connection between these two generalizations of the Nash equilibrium? Okay, I'm just warning you that nothing obvious jumps to mind if you start thinking about this problem. Okay, good. The meaning of the game can be computed very fast for large games. Okay, that's an empirical fact, and we're going to prove it. Okay, that it's polynomial time. That's open problem number 2 in the previous list, and plus really a lot of really open problems. All right. So these are my collaborators. Of this, I believe only Oliver Vigar is here. Oliver? Yeah, second row. Tall Australian. Yeah. So And Rashida Hakim and Jason Milionis are third-year PhD students at Columbia. Georgios Pilios and Kelly Spenlov is an algebraic topologist at Google. Okay, great. And finally, okay, so I have a second feature for you. Okay, yeah, very short.
Christos, before you move on,
Okay.
can you just comment or connect? So, like, another approach for dealing with dynamics in games is to look at correlated equilibria,
Yes.
which also comes from the override dynamics.
Yeah. Sure. Yeah.
And, the fact that it play repeatedly, like, why would we expect them to end up playing independently after that? It seems sort of strange. Correlated equilibria addresses that. Can you just?
Yeah. So it's an omission. Thanks, Jason. It's definitely an omission. When one talks about alternative to mass equilibrium, it's a sin not to mention correlated equilibria. Okay, defined by Aumann in the 1980s. Correlated equilibria, most of you know what it is, but it's essentially. Oh yes, sorry. That was essentially the point of departure of Roger Meyerson's talk yesterday. Okay, so basically what he does is he generalizes correlated equilibria. So what is a correlated equilibrium? You have a game, okay? There are two or more players, right? And they are thinking, what's the Nash? They cannot find it, so they're agonizing, okay? And then comes the Deus ex machina, okay? Ex machina, okay? So that's a trusted intermediary, okay? A trusted intermediary, okay? So I remember a talk by Silvio Micali defining correlated equilibria, where he had Jimmy Carter as the trusted intermediary, and he lamented how far in the chain of presidents do we have to go in order to find somebody that you can, unashamedly call trusted intermediary. In any way, okay? In any way, right? I mean, so let's not distract from this. Okay, so in any way, I mean, so there is a trusted intermediary, okay, who comes up with the distribution over the pure stratums, okay, and this distribution has the property that if the intermediary draws one pure strategy profile from this, okay, and suggests to the players, you play this, you play this, you play this. The players know where the intermediary comes from, knows that they can be trusted, knows what is the distribution, and then says, he drew from this distribution. Therefore, they make their own personal calculation and say, yep, I think that's a good suggestion. I'll take it. Okay. So that's an amazing, the amazing thing about it also is that it's a linear program. Okay, so maybe if you write equations, it's a linear program, you can solve it. And defines the polytope this kind of equilibrium. And then the point is that no regret dynamics in utility, in other words, or if you play and converge there, converge is an overstatement. They converge there in the same way that the moon converges on the Earth. Okay, it orbits around, and therefore it will converge to the center of the Earth if you take an integral. Okay, right. Okay, so Jason shakes his head. Okay, that's ominous. Okay, what now, Jason?
The empirical distribution of play is a correlated equilibrium.
Yes, that's what I'm saying.
So you resample the past.
Yeah.
Play those actions. That distribution is a correlated. It's different from saying the average position of the moon is the Earth.
Okay. You heard our disagreement. Okay, you judge for yourselves. Okay. Yeah. Anyway, okay, good. So correlated equilibria, of course, are a very attractive alternative to Nash. Okay, so and many people consider it a good attractive for Nash. Okay, so and it has some connection, even though Jason and I disagree about the details, some close connection with dynamics, okay? I am proposing sort of, especially because of the trusted intermediate problem, okay? That maybe dynamics is a good way for a good alternative. Good. And unless there are other concerns about, and other comments about the talk so far, let me go to something as something completely different. So I'm going to say, in the past decade plus, our session chairman and I have been working on sort of, on a treadmill hand, okay, so of understanding the brain, okay, and we have been doing it as faithful TCS people, okay, we have been defining mathematical models and proving theorems about them, okay, and but our ultimate goal is, to my mind, the ultimate object of the lens of computation, okay, which is understanding the brain, okay, because this is, to me, has always been, when the lens of computation became en vogue 25 years ago, the brain had always been my ultimate goal, but it takes a lot of guts, okay, or somebody or a collaborator with a lot of guts, okay, to do this. And we have, okay, so I'll tell you something. So, this is my 7th Nobel Prize winner, okay, so, in this talk, okay, so, so this is Richard Axel, got a Nobel Prize for understanding how we smell, okay, which was considered sort of a crowning achievement of neuroscience at that time. And 6 years ago, as Santos and I had been working for 6 years on the problem that he was posing with this quote, said we do not have a logic. What we are missing in neuroscience is a logic for the transformation of neural activity into thought. I view discerning this logic as the most important future direction of neuroscience, okay? And notice, Axel is the most fanatical empiricist, the most convinced empiricist I know. Okay, so he has no patience for theory. He loves experiments. Okay, and the reason, the fact that he's using the word logic, which to my mind means a formal system, mathematical system, which is ultimately computational, essentially is a white flag. Okay. Axel is asking the help of TCS for understanding the brain. I appreciate a lot, but I'm really serious, okay? Okay? I really believe that this is a TCS problem now. Santos and I and our students, we have made amazing progress, I think. Okay, so I'm going to tell you about it. By the way, here were the challenges. By the way, this is my office. During my office hours, I'm teaching a class this semester, which is the brain and computation in the brain. Okay, and the stopper. This is all true. The door stopper in my office is not working anymore, and I'm using these volumes. Okay, these volumes, as you can see, there are two different editions of principles of neural science. Okay. Principles of neural science. They're reprinted every 5 years, and there are 2,000 pages already. They become 200 pages longer with every 5 years. Okay, and if you think about it, this is a lamentable situation. This is what Axel was lamenting, that principles should shrink. Okay, that should grow. Right? When the Greeks sailed out to find the principles of geometry, they came up with 5 lines. Count them, 5 lines. Right? So this is what we need. Right? Am I clear? And this is what we did. we have taken this book and we distilled it down to 7 actions. Okay? And I'm going to explain to you this action. Unless you think, oh, I should know, okay. So I think they're very interesting. Okay? I call this the NEMO for neural model, is the world's simplest math model of the brain. Why do I say this? It's a math model. Okay, it's only 7 lines. Why is it the simplest? For 2 reasons. If you take any line and you omit it, we can prove you cannot do anything interesting. Okay? Except for the last line, long-range inhibition. You can do something interesting without long-range inhibition, but long-range inhibition is you need in order to get universal computation. Okay? And if you take any single line and you try to simplify it, I bet you cannot. Okay? We have the simplest version of each line. And so I'm selling it as the world's simplest model of the brain. The question is, can you do shit? Okay, you know, that's the real problem. That's the real question. So let me explain quickly to you what these lines mean. Okay, so no, it will take me 5 minutes, but pay attention. Okay, so you know it's a lot of so intuitive details, but details. Okay, excitatory neurons. Okay, these are the neurons that fire. We assume that the brain consists of excitatory neurons. Second line. We assume that these excitatory neurons are divided in brain areas. So our brain has about 100 areas called broadband areas. Okay, so you know we don't mean this. You know they may be slightly different, but yes, I mean they're divided into brain areas, into areas. Each area, let's say, has 1 million excitatory neurons. Clear? Okay, so far. Okay, it gets tricky. Within each neurons, you have Erdős-Rényi synapses, directed edges between these neurons, okay, with small probability. So this is the connector. This is unrealistic. We know well that the synapses in the brain are not Erdős-Rényi, okay? But we believe it's not unrealistic in a distorted way, okay? So no,
Is this in each area separate?
in each area separately, yeah.
Not between.
No, yeah. But now I come to you. The next slide is between areas, between certain pairs, directed ordered pairs of areas, there is going to be a bipartite GMP graph. Okay, we call this sometimes 5x. Okay? Everybody's following so far? If you have any questions, ask. Fifth line. The firing comes in discrete steps. They fire in unison. Okay. This is every neuroscientist knows that this is not realistic. Okay, if a neuron fires wherever it wants. But we have met no neuroscientist that says this is. I don't believe this. This is the Achilles heel of your model. Okay, it's not distorted. Okay, I mean it's fine. There is in-area inhibition. You know, that line hides the heart of our model. Okay, what's this line? So pay more attention. In every brain area, there are inhibitory neurons. They're the firefighters. They make sure that you don't get seizures. Okay, so when the excitatory neurons get excited, the inhibitory neurons go to work. They get excited also, and they silence them. In the beginning, they silence too many of them, and so most firefighters go back to the fire station. But then the excitatory neurons get more. Okay, so there is a damped oscillation that ends with something called the excitatory inhibitory balance of the area. Okay, so we model this by saying, okay, that's where the crucial math comes in, that out of the 1 million neurons in every area, at any point, only 10,000 will fire. That's the number K. Okay? Which 10,000? Now comes a long mathematical sentence. The 10,000 neurons among the million which receive synaptic input from the previous step, that is among the 10,000 largest. Okay, in other words, for every neuron, we say which are its presynaptic neurons, what are the weights of the synapses, which of them fired, add this all up. And in each area, pick the 10,000 numbers that are the biggest among the million. Okay? This is, I mean, if you understood it, you should feel uneasy. This is the part that makes computer scientists uneasy, because it looks like a non-local operation. It looks like a lot of work. But but explain to you why it's not local. I showed you the physical, I described to you the physical system that produces it. Okay, it is the interaction, and it's an ODE between inhibitory and excitatory neuron. Okay, and you can solve this idea. You can solve it analytically, and it gives you that number K. Okay, and these are the ones that will end up fire. All right, so that's inner inhibition. Finally, Hebbian plasticity. What's Hebbian plasticity? It is the synapse. Every synapse has a weight. Okay, it goes from A to B, and there is a weight. If at the time T, this neuron fires, and at the time T+1, this neuron fires, the brain is happy. The brain is happy with this synapse. Okay, and rewards it, let's say, by 5%. Okay, so it says, I will increase your weight by 5% because you caused a fire, and I'm indebted. Is it clear? No, the brain seems to like neurons firing. Okay, is it clear? That's it. There is one last thing, which is sort of a frivolous computer science. It's the control structure of this hardware language, and basically we have other areas outside these areas, which are inhibitory areas. And these areas can inhibit whole areas. So at some of these steps, the whole area may not fire at all. Okay? Or they can inhibit other inhibitory populations. And now they disinhibit some areas. Okay? So you have this extra, which allows you to do combinatorial programming. That's it. Of course, if you are interested, there is no backpropagation, okay? Right? Because we are not trying to beat ChatGPT, we're trying to find out how the brain works. This is a dynamical system. And the amazing thing is that we can simulate it approximately extremely efficiently. Stable representations emerge. Remember, so these are the register values of the chip, and you can compute with this. Few short classification learning you can do. You can memorize sequences. You can do universal computation. You can write a parser of natural language in this language, and sort of what knocks the bottom out of it, in my opinion. You can do basic language acquisition. You can build such a system that learns natural language. Okay, so you can find, if you are interested in this, you can follow us on Google Scholar. You can like us on Google Scholar. Okay, so this is the Nemo team, and Max is graduating. This is all marketing. Thank you very much. Ask a question.
Yes, we have time for questions.
Just 1 second. The Hebbian, whatever it was, so weights just increase?
Good point. Okay, so no weights. So the question. So your last question is weights only increase, so they become infinity. Two answers. Okay, one is that there is another mechanism that normalizes. Okay, so second answer, we only run it for a few seconds, so we don't care. We don't run this feature.
So I have a vivid memory early years when I had private conversation with you on a fixed point, and you basically say there are two different kind of fixed point. One is ground one, right, which is topological. One is basically defined on that, the sink, right? So clearly now you're talking about the cycle, the cycle thing.
Right.
So that I vividly remember you said something very interesting. You said those topological fixed points are really hard to compute because locally you have no way to compare when you're making progress. However, the dynamic base, because they're potential function based, they somehow, because they have potential values, you can do local search, local gradient style. So is the one with the same will also, in some sense, more efficient to a larger degree because they are closer to this loosely potential based
Yeah. Yeah. So I mean, every intriguing thought you share comes back to haunt you. Okay, but you know, I'm still, you know, I still believe that, and maybe subconsciously this thought guided us to this work. Yeah. You guys are really hungry. You really want to go to lunch, right?